Hello! In today's webinar, we will review many of the most important changes in the Java platform that have happened between the release of Java 8 in 2014 and JDK 18, the latest version currently available. Up to JDK 8, Oracle's release model was to make one version of the JDK available to use in production at no cost, but with certain restrictions. In this graph, those are the releases in blue. When a new release came out, there was about 1 year of overlap and the old release reached end of public updates. Further updates would then be hidden and require a login and a password to access. Those are the releases in red. Only customers with a login and a password can see those updates. With the release of JDK 9, we announced a change in our release model and in our licensing. Instead of 3 years or so between releases, we switched to a model of a feature release every 6 months. Now, if we try to support all of those releases for a very long time, we would end up having too many releases. So we borrowed a page from other technologies and decided to provide long-term support only to some of those releases. JDK 9, having been developed under the old model, needed the usual stabilization period, in this case, to be provided by a couple of feature releases rather than minor updates. So JDK 11, 1 year after JDK 9, was designated as the first long-term support release. The license change was to expand access to our update releases past the time when they would otherwise become available only to customers. When JDK 8 reached what would normally have been the end of public updates in 2019, we didn't place further updates under login and password as we had done in previous releases. Instead, we made those updates available for personal use, for development use, and for running Oracle products. But you do need a commercial license to use those updates in productions. Those are the updates in green. The new release model worked pretty well from a development point of view. For the next 4 years, we produced feature releases like clockwork. But we got feedback from our users that having only the last version available under a permissive license didn't give our users much chance to enjoy the benefits of the LTS releases, and that LTS releases were too far apart. With JDK 17, the second LTS release under the new model, we announced 2 more changes. The first one is that, given the high quality of the releases and the desire to be able to adopt LTS releases faster, we should start offering LTS releases every other year instead of the original plan of every 3 years. The other change is that JDK 17 and later versions are released under a new license called the No Fee Terms and Conditions, which does allow its use in production. Updates for JDK 17 will be released under that new license for the first 3 years. At the end of those 3 years, once a new LTS has been available for a year, we will switch back to the Java SE OTN license for further updates of 17. It's worth notice that all of the updates, including the ones under the Java SE OTN license, are also available without having to purchase a Java SE subscription for Java workloads running on Oracle Cloud Infrastructure. 6 months between releases doesn't mean that we managed to produce the same amount of work that used to take 3 years in only 6 months. Releases got much smaller. Here, we can see how many JEPs, that stands for Java Enhancement Proposals, have been delivered in the last 8 years or so. If you group then on LTS releases, you will see that the number of changes between LTS releases is comparable to what we used to have on the major releases of yesteryear. Now, before telling you about the new features added in later versions, let's quickly review things that have been removed or deprecated, since those are the ones most likely to be the reason why some of our users have not yet taken advantage of the newer releases. To avoid surprises, features are never just removed in a major release. First, they're deprecated, and only after a reasonable number of releases, which depend on how widespread the feature was and how good are the replacements available, will the feature be removed. The 2 first ones, marked here in blue, are the ones most likely to trip users going from Java 8 to a later version. JDK internals are now inaccessible out of the box. Internal APIs were never meant to be used and can be changed or removed even in update releases. Still, many frameworks and app servers relied heavily on them for many reasons, some more valid than others. In JDK 9, we started the process of providing fully supported APIs for most of the valid cases for which developers were relying in internal APIs, and we started making it harder to use the internal APIs. JDK 9 only had warnings, same thing as we had in prior JDK versions. Then with JDK 16, illegal access was disabled by default, but you could turn it back on with a single command line. Starting with JDK 17, there is no single command line to enable access to all internal APIs. If you insist in using internal APIs, you now need to list each package where you want to allow access to internal APIs separately as a separate option in the command line. So you should expect to have to upgrade your tools and frameworks that you are using in Java 8 to adopt later JDK versions. The next change in order of potential disruption is the removal of Java EE technologies like JAX-B and Corba. Those no longer ship by default with the JDK, but they are now instead made available as a separate download. In most cases, the changes to the code that rely on those classes is that you will now have to import a library and refactor the import statements. The rest of the changes are mostly about tools that were not widely used, or that have been superseded, or that never really worked the way that they were intended to, and they were causing problems for the maintainers of the JDK, as they had some complicated interactions with new or with planned features. The list of deprecated for removal are features that are still available in JDK 18, but that will be removed in some later version. There was also a couple of experimental features added in JDK 9 and 10, which didn't work out as hoped and have been removed in JDK 17. We'll continue a review with changes to the Java language, which are always a favorite of developers, as these are some of the changes with a larger impact in how most developers code. And it's always fun to discover an easier way to do a task. We will not go into much detail. There are plenty of other presentations that go into each one of these releases with a lot more detail. My goal is just to whet your appetite and help you decide which features you want to learn more about. The language enhancements come from Project Amber in OpenJDK led by Brian Getz. Amber aims to simplify data-oriented programming in Java by making it easier to write correct code while keeping the type safety that developers rely on. We're taking advantage of the 6-month release cadence by previewing most language features before getting them added to the standard. Preview features ship in the GA release, but are disabled by default, so there is no risk of anybody using them accidentally. As you can see in this chart, we have been averaging 2 previews for each feature, but it's not a hard rule. Local variable type inference was already well understood and didn't need any previews. Conversely, although it's not in this slide, pattern matching for switch will come back for a 3rd preview in JDK 19. Let's take a look at these features briefly. When you have a local variable that is declared and initialized in the same line, it is redundant to have to declare the variable type, since the type can be easily inferred from the initialization. Avoiding the type declaration can lead to more readable code. Of course, if abused, it can also lead to harder to understand code. But then again, some developers have managed to write hard to understand code even without this feature. And since its use is optional, we decided that the benefits outweigh the risks. We also published a pretty comprehensive style guide that will help you identify the potential pitfalls and the right places where you should use type inference. With JDK 14, we introduced switch expressions. Now it's pretty common, or actually was pretty common, to write switch statements like this, where it is clear that it really wanted to be an expression. You can see the variable at the top, outside of the scope of the switch, then a value set inside each one of the arms, and it's returned at the bottom. There's a default clause, and there's breaks everywhere. This is clunky. Using a switch expression, we can return a value without having to declare an extra variable. Another improvement is that now we can have multiple constants separated by commas for each branch. Finally, the cases in a switch statement must be exhaustive. You have to provide a path for all possible values. which normally means that you have to provide a default, unless you're operating on an enum, in which case, like in this example, the compiler can check and make sure that you have covered all of the valid use cases, and then you can get rid of the default clause. Text blocks were introduced in JDK 15. They're multi-line string literals that can be represented in code without having to deal with those escape sequences and clunky concatenations. Multi-line strings have always been sort of painful in Java, but we use them in most programs to store snippets of, say, JSON or SQL or HTML or XML. A text block is a two-dimensional string literal denoted with a triple double quotes as the delimiter. It can span multiple lines and obviates the need to use clunky concatenations with escape characters for new lines. The new method formatted added to the string class works like string.format, but produces code that it's easier to read. In this text block, the white space under var HTML is considered incidental indentation. The compiler strips it away so that the code can be freely reformatted without changing the string denoted in the text block. JDK 16 introduced record classes. Now, many classes are dumb wrappers for data. In this example, the only part that we really wanted to say is the part in green. You want to declare a class with a few immutable fields and then use it to pass around the structured data. But you will need a constructor, you should create an equal and a hash method, and it would be great if the toString showed us the values. Now, IDEs could automatically write all of these boilerplate for you, but you would still need to review it every time you wanted to maintain the class, just to make sure that there's nothing relevant there. All of that goes away with record classes. A record class is a final class that serves as a transparent carrier for data. The data is spelled out in the header of the record class. Constructors and getter methods and equals and hashcode and toString are all provided automatically. The data is immutable, it's stored automatically in finite fields, so there are no setter methods. You can write your own methods in a record class if you want to do more than just that boilerplate. Say, for example, you wanted to include some validation in the constructor, then you only write the constructor. And then when you review, you know that everything that you're seeing actually does something useful. JDK 16 introduced pattern matching for instanceof. Now take a look at this code. We have all written code like this. It looks so simple that we often miss all that is going on here. We have three things happening at the same time. We're testing to see if the object is a string, and then if it is a string, the next set of instructions is a given, right? You will have to define a variable of type string and then cast the object into that variable so that you can do something useful with it. Using pattern matching, we can reduce the code into a single line of code that does all of those three things at once. In this example, the variable s is only created if the object is a string. If so, the object is automatically cast into that variable, and the variable is in scope only inside the brackets of the if statement. If there were an else part of the conditional, the new variable would not be in scope in the else part. Seal classes and seal interfaces restrict which other classes or interfaces can extend or implement them. This provides a more declarative way than access modifiers to restrict the use of classes or interfaces. In this example, we're defining a shape class and dictating that it can only be a circle, a rectangle, or a square. No other types are allowed. The subclasses of a seal class may be final, like circle here, or they can be sealed themselves, with its own list of subclasses, like rectangle, or they can be non-sealed, like square, so that anyone can extend those. Sealed classes allows us to better model what we had in mind when we created this hierarchy. JDK 19 is the third preview of pattern matching for switch. Switch statements worked on a few types: numeric, enum, and strings. If we wanted to use patterns to check for a certain number of possibilities, we need to use a chain of if-else statement, like we have written here. Using pattern matching in a switch, we can make this much clearer. Remember that the case statement has to be exhaustive, so that in most cases you will need to add a default value. There's one thing missing here though. Traditionally, switch statements and switch expressions throw a null pointer exception if the selected expression evaluates to null. Testing for null is done outside of the switch statement. But now that the case labels allow for type patterns, we can add a null case into the switch statement, making the code easier to read and to maintain. After a successful pattern match, we often need further tests, which can lead to some cumbersome code like this, where you have the switch and then an if statement nested inside. We can improve readability if the pattern supports a combination of pattern and Boolean expression. So, guarded patterns allows us to write in a cleaner way. Be aware of the order of the case statements. If I were to invert the case statements, the first one would catch all strings, even those of length 1, which means that the second case would never be reached. That would produce a compile time error. We've changed the way that we raise null pointer exceptions. We now give you more information, because null pointer exceptions can occur almost anywhere in a program. And many developers rely on the JVM error message to pinpoint the source of the exception. Before this enhancement, the JVM would just print out the method, the file name, and the line number, like what we see here. If the line has just one variable, then all is good. But for more complex cases, like in this example, it can be hard to pinpoint which variable is null. Since the JVM knows this, we can have it give us a more detailed message. Now, not all the changes are in the language. Let's take a look at some of the new tools that have been added to newer JDK versions. Before we can talk about the first tool in our list, we need to do a very brief overview of one of the impacts of the modularization on the Java SE platform. With JDK 9, the Java platform has been modularized. Instead of a large monolithic runtime, JDK packages have been arranged into modules. Modules allow for a clear encapsulation of responsibilities and establish a formal dependency between them. In this graph, we see only the Java SE modules from JDK 9. There are other modules in JDK 9, the JDK modules, but this graph is good enough to illustrate our point. JDK 9, with all of its modules, is about 300 megabytes. Imagine if we had an application that only requires APIs in a couple of those modules. Let's say SQL Rosette and Java Activation. Now, you cannot just use those two because there's a transitive dependency on other modules, so your application would end up depending on all of the modules that we've highlighted here. If you were to exclude the modules that your application doesn't use, you could create a custom runtime that would be about 1/10 of the size of the complete JDK. Okay, that's all that we needed to understand for this parenthesis. So, there's now a new tool that does exactly what we have said in the last 3 slides. jlink can create custom runtimes that can be used when an application is expected to be the only user of the runtime. This is ideal for containerized applications, since you normally dedicate a new container to each new application. If your application has been modularized, then the system can automatically determine which modules it will need, so you can easily create a custom runtime that includes all the modules you needed and even your application. If your application was not modularized, then you need to somehow figure out which modules that application needs. That could be a lot of work if all you have is the bytecode for the application. What we really need is some way to determine which modules are required by any application, even non-modularized ones. So of course, the next tool is the Dependency Analyzer, which gives us exactly that. It's a tool that tells you which modules your application needs. You can also use it to determine if your application relies on JDK internal APIs, since, as we explained at the beginning, those could be a problem with later releases. Now, jlink solves part of the deployment puzzle. You can create a smaller runtime and application combination, but developers still need to package the custom runtime and the application into an installable bundle for end users. That's where jpackage comes in. jpackage bundles the application and the runtime into a self-installing package in a format that is consistent to the users of your supported platforms. So if you're using Linux, you can get an RPM or a Debian package. If you're using macOS, you'll get a DMG or a PKG. And Windows users can produce an EXE or an MSI. It can generate, the packet, the installers created by by jpackage can create desktop shortcuts. They can create start menu items, set file associations, and you can create multiple launchers per package. This is one of the tools available to take advantage of modern deployment models. JDK 9 also introduced JShell, which is a command line tool that lets you quickly explore Java APIs without having to compile your code and with a simplified syntax. It has tab autocomplete, and it makes it much easier to play around with different methods and classes without having to set up a development framework and without requiring any third-party IDEs. For simple programs that fit in a single file, JDK 11 dispenses with the need to compile using Javac before running the program. You can call a Java class directly from the command line. It is also possible to use external libraries, as long as you pass them as parameters during lunchtime. Before JDK 11, Java File Recorder was a commercial feature available only to Oracle customers. With JDK 11, it has been open sourced and it's now available to everyone. It allows you to monitor production systems because it has a very low overhead, so you can just have it running all of the time. It has been used and loved by the Oracle support team for decades, and it can now be used by all Java developers and system administrators. Until JDK 14, you had to create a recording file, which was then passed on to JDK Mission Control for analysis. With JDK 14, you can now stream events from a running JVM. Now, there's some improvements as well in the libraries. Let's dig right in. JDK 11 introduced an update to the HTTP client. This update is now asynchronous. It implements HTTP2 interface. It supports non-blocking requests and provides better traceable data flow. Before JDK 9, it was cumbersome to create immutable instances of list, set, and map. You can see here in the code, it would take multiple lines and you have to first create a set and then make it immutable using the collections and modifiable set. With JDK 9, we introduced a one-liner create and populate small collections. In JDK 18, we still have as a preview, we have it in incubator in JDK 18, it's going to be in preview in JDK 19, the new foreign function and memory APIs. These are APIs that will allow a Java program to call, to read memory outside of the Java heap and to use C libraries in your Java applications. Now, you could always do this before using JNI, but that required that you use different tools chains for different platforms, and it was brittle. So using these new function and memory APIs, you can make that much easier. So JDK 9 introduced deserialization filters, which allow you to specify which objects can be serialized and which objects should be rejected. This is a good measure for improving the security of your applications. The original concept was further improved in JDK 17 with JEP 4.15. Now, this is the one feature that I'm listed that was considered so important that it has been already backported, and it's also available in the later versions of JDK 8. The features that I've listed so far, you only get the benefit of them if you're rewriting applications. It makes it easier to rewrite something. But improvements in the JVM mean that there's also benefits to be had if all you're doing is running an application that was compiled in an older version of the JDK, and now you're just running it in a newer one. Let's take a look at what has happened between JDK 8 and JDK 18. This is for one of our internal benchmarks. you can see here the startup time of a very simple HelloWorld application. It got slower with the introduction of JDK 9, and that's because when we modularized the platform, there was some work to be done before the first line of code was read. You had to resolve the module system. So the startup time got worse. However, only a year later, with JDK 11, we had improved on that to the point that it was now faster than what we originally had on JDK 8. And that continues to get better across releases, as you would expect. If you happen to be using Lambda expressions, then this is even more dramatic. Lambda expressions introduced in JDK 8, same deal. The first time you use a Lambda expression, you need to do a lot of extra work, and that meant that the startup of an application, if you used Lambda expressions, got actually pretty bad. The startup of an application with Lambda, I mean, it's pretty fast. You're looking at this in milliseconds, but it's still more than doubled. Still, same idea. You can see by the time we reach JDK 11, the startup time for an application using Lambda is faster than the startup time for an application using Lambda in JDK 8. And you can see that the difference in startup times keeps reducing. In some cases, we introduce new capabilities. The JDK had JDK class data sharing all the way from JDK, JDK 8 already has JDK class data sharing. With JDK 11, we introduced the class data sharing capability for the application classes. And that meant that if you use that, the startup could be dramatically improved. So on top of the descending startup that you see here from the JDK itself, you can see a nice drop if you turn on app class data sharing. There are other places where we've improved performance. For example, compact strings. We realized that on most of our programs, the ones that are not using Asian locales and multi-byte strings, when you store a string in memory, we used to have 2 bytes, and the first one of those, well, multi-byte strings, the first byte was always 0. So by compressing that, we don't lose any capabilities. We use less memory and we improve performance. In this diagram, we see how native memory usage has decreased, even when using the same garbage collector. Now, you should expect to see these benefits without having to change anything in your code, just by updating to a newer Java version. So you can see here, the blue is JDK 8, and you can see how it decreases over time with each new release. For more dramatic changes in garbage collections, we go to a new garbage collector. setGC was added as an experimental garbage collector for Linux in JDK 11. It was added to Windows and Mac with JDK 14 and was moved from experimental to supported in JDK 15. These diagrams showed the garbage collection pause times for some of our benchmarks running in JDK 17. It compares the default GC, which is G1, with the newer collector, setGC, which focuses on minimizing garbage collection pause times. Keep in mind that these lower pause times are offset by slightly larger memory usage, so choose your garbage collector wisely. The scale here is in milliseconds, and we see that the G1 has an average pause time of about 150 milliseconds and a max pause time of about 450 milliseconds. Looking at setGC, it looks like there's no pause times at all. However, there are some, it's just that they don't register at this scale. So I'm going to zoom in by a factor of 1,000. Then it looks like this, and we can see that setGC indeed has pause times. With the scale now in microseconds rather than milliseconds, we can see that setGC has an average pause time of about 30 milliseconds and a max pause time just below 200 milliseconds. This is well below the 1 millisecond max pause time that was our target. Also, note that while the setGC pause times are constant, we can still see that there's some variance. This is because setGC is still at the mercy of the operating system scheduler, so things like scheduling latencies, interrupts, and etc. can cause post times to vary a bit. The huge difference between setGseed and G1 is now becoming even more apparent. Here we see, by the way, the GC post times, how they improved over time using the same benchmark. JDK 11, the max post time was approaching 5 milliseconds. And that was pretty good, much lower than G1 post times, but not quite the goal of sub-milliseconds. Fortunately, the post times have continuously been improved in later releases. In JDK 16, the pauses became constant and well below 1 millisecond. Now, this presentation covers just a few of the JEPs in the releases between 8 and 18. If you want to see them all, or to learn about each one in detail, you can go to openjdk.org. Each release will include a list of all of the JEPs that it delivers, with a technical and detailed explanation of the features. If you prefer interactive sessions, and you would, that's why you're here, then you can take a look at some of our videos in our YouTube channel, or look at the pages that our developer evangelism team maintains. Finally, if you want even more, come see the latest sessions live. Java 1, the premier conference of Java developers, is back, this time in Vegas. Registration is now open. With that, we have finished the recorded portion of the presentation.